Hi everybody, so I want to come back to what we talked about. We talked about diffusion mechanism and we face a problem. For example, I want to give you this thing. So we have, for example, the human airway, and we're talking about drug delivery concept. So a particle at location T, because of gravity, because of drag force, would find himself in more advanced time, T plus dt, here. However, because of the randomness of diffusion, remember that we need to add this term, okay? So each iteration that you are doing, okay, think about step by step by step, you need to add this accumulative effect of the jumps of the particles, the jiggling effect. But unfortunately, we realize that this is the formula for the distance, and I want to remind you, it's absolute value, okay? So it could be negative, positive or negative, right? So you don't know it. So here I put absolute value, so plus minus here and plus minus here. You should add to your simulation a randomness function. But the question remains is, what is this d? What the value of this t, of this d? So the goal of this tutorial right now is to extract this d, okay? And the one and only the annus miracle year 1905, Einstein managed to do the impossible thing, and he published 4 different papers, each one in other field. One in special relativity, dilution of time, another one, photoelectric effect, which he got a Nobel Prize for it, the mass energy equivalence equal mc square, which is most the famous equation in science. And not but least, he also published a paper about fluid mechanics. He published a paper named On the Motion of Small Particles, like the one we inhale into the lungs, suspended in stationary liquid, which means no flow, as required by the molecular kinetic theory of heat. And he found D, and also found Avogadro number, and a connection between them, which means you can do experiment, measure D, and then you can calculate Avogadro number. And that was a huge hit. Why it was a huge hit? Because at that time, you know, atoms were very, let's say, not a popular idea. Okay, the idea of atoms came from the early times, from Democritus, 300 BC, and where time passed, people start to believe that the world is built of small, tiny unit blocks, which called the atoms. However, in Einstein's time, this was not the popular idea. And Einstein was kind of a rebellion with that idea and few others. So what Einstein said, he said, you see this random motion of particles, the big one in the air or in the fluid? So maybe this is a result of a smaller particles that jiggling around crazily, okay? So that was the idea, and I brought a funny demonstration to show you this concept, so if you can join me, and you too. So you can think about this axis, okay, as the x-axis, which means diffusion can take me here, or can take me here, right? And the random collision of molecules, actually that's the one that produced this jiggling motion. So come. I'm going to be in this side, you're going to be that side. This is your weapon. Use it carefully. I took the strong rubbers to myself. Yeah. So in general, if this is a big particle, we're talking about 1D, yeah, extended to be 2D for us to do a better extent. But come here. So you ready?
What are we supposed to do?
You're supposed to hit this particle.
Okay.
You see? So start.
Yeah.
Okay. You can be closer.
Okay.
Okay, even like this. Go ahead. Okay, so it starts to jiggling around. We are really bad. Oh, you see? It starts to jiggling around, move to different locations. Oh, this was a good one. So, okay, that was great. Okay, we won, but okay, that was great. Okay, so the main idea that I want to show you is this randomness of air molecules. It's what driving this mechanism. So that was the idea of Einstein, and he came up with some solution for that. And we could validate this experiment, and actually Einstein proved that atoms exist. because he took into assumption this effect, this atom, this randomness, and he can measure Avogadro number. We're going to saw it, it's going to pop up in the equations, and that it means that there's atoms. That's the idea, and this is a really blessed thing that happened to humankind, so I hope you're ready to get our Nobel Prize as well. And my first question to you is, what is the characteristic time scale between collision of air? Which means in our analogy, what is the time that rubber fly in the air until it hits something, okay? So let's go to the board. We are here. We are in question 2a. What is the internal time, which means the time between collisions, for air at a room temperature, okay? So we are looking for time. How we can find time? General idea? What ratio can give me time? Definitely. So if I know distance, and I know some velocity, I can calculate what is this time. So what is the distance of molecules in the air? We learn about this. Remember the name of that? The mean free path. We learned about that in the previous tutorial. So this distance is lambda, and lambda is equal to, in room temperature for air, is 6.8 10 to the minus 8 meter, right? But what we can do about the velocity? Let's do it in red. You're going to see soon why. This is a more complicated thing. I gave it to you as a given thing, but there's a formula I can show you, okay? If you want, write in the comment and I will upload the formula. Actually, it's a good question, okay? But what is v? What is the velocity? So for that, I need to introduce to you Boltzmann. So I put in this picture, let's go to the television. So Boltzmann, this guy here, came up with kinetic theory of gases. And he also believed in atoms, okay? He was also a unique guy. And he came up with this equation. He said that the average velocity of particle, you see this average sign? Squared, look, it's a 3D problem, okay? So the average of all the direction of the velocity, you see the kinetic energy, is equal to this term, which is the Boltzmann constant, which is just a number, and the temperature, okay? So how much hot the fluid is, the faster the particle is moving. So let's take this idea here. So Boltzmann said that kinetic energy is equal to thermal, it's derived from a thermal energy, and the kinetic energy is half the mass of the particle we're dealing with, air. So we need to think about what is the mass of air, of a particle of air. And here it put the velocity squared, and I want to remind you this is the 3D velocity magnitude, not 1D. Okay? And for that you have 3, which related to the 3D effect, divided by 2. Boltzmann constant, the temperature, which we both know for the room temperature. This is 298 Kelvin. 8 is looking like this. Yeah. Boltzmann constant, it's 1.38 times very small number, joule per Kelvin. This is actually the constant that switch temperature to energy, joule. You see it? Okay, and the mass of a particle, how we can calculate the mass of oxygen, approximately? We can say the mass of oxygen, again? It's a single particle, okay? So you cannot tell what is the density of a molecule because you need a volume for it, yeah? But we can do something, M equal to 20% of the air is oxygen, right? The mass of single oxygen molecules. And plus, 80%, the mass of, what is most of the air consist of? Nitrogen, right? And this is going to give us that the mass of this particle, let's put it MP, so we'll not forget it's not a specific volume, it's a specific particle, is equal to a very small, small. And for me it was very surprising, because when I saw this, when I calculated it in the past, I thought to myself, wow, this particle doesn't have any momentum at all. Look how small it is. It's a molecule, right? How this collision affect the world, right? It's so small. You know, it's like a fly that hits a truck, a ship, a cruise ship. Think of the mass of the particle, of an air source, versus the mass of a molecule. This is a joke, right? But something very interesting happened when you take this equation, right? Let's put it here. So if I'm gonna try to get our velocity, average velocity, we're gonna get it equal to 3kBt divided by m. You see that the m is in the denominator? So if we're gonna plug everything in, you're gonna get a crazy velocity. I'm not joking around. Half of kilometer in a second. And this is not the fastest. This is the average. You see what I mean? So it's very confusing to think about that, but the rubbers that we have don't have a lot of mass. This one. They don't have a lot of mass, but they have a huge kinetic energy. And for that reason, they can move the big particles. That's why I love this demonstration. If we're gonna go back here and plug the velocity, 500 meters per second, we're gonna get a ridiculous time. We're gonna get 0.1 nanosecond. 0.1 nanosecond. What does it mean? It means that every tenth of a nanosecond, boom, 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 the particle will get hit. Sometimes with this velocity, sometimes with smaller velocity, sometimes with great velocity. And this thing average out when the particle is big and you have a lot of collision. But when the particle is very, very small, it's not that even. Suddenly, it got a big bump from the left, and sometime from the right, and from the left, and twice from the left, and twice from the right. And that's the reason we see this jiggling motion only for small particles. You see what I mean? Great. Okay, back to the TV. So if you're going to add the particles, we're going to see that the particles, the small particles, is actually what doing this Brownian motion. And we are interested in finding what is the location of particle in time, okay? And this is not a joke, okay? So let's find it. It's not a joke because somebody got a Nobel Prize for it. I don't say it's going to be easy, okay? But let's try, okay? Let's use our intuition and try to build it, because I believe that if one man can do it, everybody can do it. Okay? So my question to you is, what are the terms in Newton's second law? Okay? Let's derive Newton's second law on a particle suspended in fluid. So stay with me. So Newton's second law is F external, right, equal to dp dt, right? And we're going to do it only in the x direction, okay? And of course, we can do the conclusion later on, okay? You know, let's start with the vectors, and then we're going to omit the vectors. Okay, so help me, what are the terms in Newton's second law? This side is easy, right? We know it. It's the change in mass of the particle, right? Multiplied by the velocity of the particles, plus the change of the velocity multiplied by the mass of the particle, right? We're going to assume there's no changing in the mass of the particles due to the collision. So this is one side of the equation. This is this. Here, there are two dominant forces. Maybe you can help me. So what do you think there are the forces on a particle in a fluid? Again? Great. Some random diffusion force of particle pushing around. So this is the most complicated stuff. So let's do FB. It's a function of t. I don't know quantum mechanics. It's too complicated to the humankind. This is a stochastic force, which means the force is positive, very strong, then it's become negative, then it's become super strong, then it's negative. And every change that you see here is 0.1 nanosecond. Okay? Very complicated. Big problem. Very big problem. Okay? You start with the hard stuff. What is the easiest stuff? What else happened in a particle inside fluid? Definitely. The particle start to move because of the pushing, but there was already particles, there's a fluid around, and we know that particle in a fluid find it hard to move because of the resistance of the fluid. The fluid want to stay in place. So here we have no other than the drag force, and let's do a short reminder. If we are talking on a very small particle, which means the flow around the diameter of the particle is very, very slow, not slow, but has a Reynolds very small, right? It can be not even small, but smaller than 1. We can approximate the drag to what we called as Stokes drag. Stokes drags looks like this: 3 pi mu of the fluid, dp, the diameter of the particle, and if you are dealing with small particle, there's experimental correction, which called CC, Cunningham pi factor, and it's dependent on the velocity. Independent on the velocity of the flow is pushing the particle, and also on the velocity of the particle at that moment. We're gonna assume, like Einstein did, that the flow of the surrounding is 0, okay? Which means all the movement of the particle is due to this random force, okay? And of course, it's very easy to add this term or add gravity or add all the other forces, okay? But the hard stuff is here, okay? This term here, we learned a funny name, right? That can present it. Remember what is it? What was it? This called the 1 over the mechanical mobility. This is 1 over the mechanical mobility multiplied by velocity of the particle, and here we have a minus. So if you don't want to write a lot, this whole term is the mechanical mobility. Got it? Minus? It's minus because of you. Okay? So this. Got it? Okay? So this is the terms. And now I want you to tell me, I'm gonna go here. I want you to tell me why is the original ordinary, the equation that we have cannot be solved. Okay, so we got this thing. If you want to have, let's write it in an organized way, right? So we can do it already in 1D. We have m dx dt, right? Is squared, the second derivative. We have the random force, which is pain in the s, and we have the drag force, which is the inverse of the mechanical mobility, multiplied by the velocity, right? Du dx, right? And my question to you, by the way, we can reorganize the equation. We can divide it by the mass, right? M, and if you're gonna multiply m by b, you're gonna get the relaxation time. Okay, this is by definition, right? B, d multiplied by m is the relaxation time. The definition of the mobility is actually the mass divided by relaxation time. Just a reminder. Okay? So this is a second order ODE, and why this solution is not solvable? Exactly. So if you're going to think about it, the solution of x is the homogeneous solution, no problem. I can find the homogeneous solution. We learned it is kind of an exponent, right? Remember it? But the private solution is definitely not a constant. And I cannot guess it. So I screwed. Nothing I can do, okay? So that's where all the people in the world was until Einstein came. And Einstein came with a very cool idea. So we realized, okay, based on our mathematical intuition, we know the solution should be related to the average of x squared, right? Rather than x. So this is equation of, you see it? As x. So derive this by multiplying the equation by x. So what we're going to do, we're going to take this equation and multiply it by x. And then we're going to do an average, using a time average to eliminate the difficult terms. And the method that I'm going to solve today is, it's based on Einstein idea, but I'm going to show Pon-Lagvin way of solving it. Like, Newton derived all the equation, but we actually use Leibniz notation. So the one that invented is not the one that know how to market it best or to make it easy to use for the community of scientists. So most of the time, people show his derivation and not Einstein, which is less intuitive. Okay, so let's do it. So we're in section D. I'm going to clean this thing. We're trying to multiply the equation by x and present it as function of x squared. As much as x squared as I can, because I know the solution to the dynamic of the particle is related to the x squared, because I don't want the plus and the minus to cancel each other. We saw it in the mathematical derivation. So if I'm going to take this equation and multiply it by x, we're going to get, let's have another marker. Here it is. So we're going to get x times d square x dt equal to x multiplied by the random force divided by m minus 1 over tau x dx to dt. We're in section D, right? We want to simplify the equation. Actually, it's not a simplification, but present it as x squared. And the hint was that you should multiply the equation by x. Okay, so we did that. I know it looks weird, why we should do that. So the reason we did that is I want to replace that term and that term with other terms that include x squared. So this is simple identities. You don't need to remember it, you just need to recognize it. But the reason I do it is because I can get my x squared back to the business. While here I don't have any x squared, so this thing, this multiplication, you can check it, is equal to that. The second derivative of x squared and this correction that you need to put. And for that, I can change it to x squared very easily, half dt x squared. You can check that if I'm going to derive this, it's going to be x multiplied by the eternal derivative of x, and I'm going to get 2, so I put half to cancel it. So using these terms, I can finally have my equation. And I want you to notice something. What is this? What is dx to dt? The velocity of the, okay, the location of the particle in time. Great. So what we get here an easier equation, x squared dt squared minus up squared equal x fb t divided by m of the particle, of course, minus 1 2 tau d to dt of x squared. I like it. So what I want you to see is at the moment we have here x squared. We know we are in the right direction. It's good, but on the other hand we kind of screwed, because we have this term which we need to get rid of, and we got this term which is not dependent on x squared. So it's going to do problems, and we still don't get rid of the force, the Brownian force, the random force that we don't know. So what was the genius of Einstein? So Einstein thought about it and he said, the average of the movement of the particle is 0. I must use this idea and then I can get rid of that. Okay? That's the concept. So he wanted to average the problem, but remember that we don't have many particles as we had before. We did an average of the group. Now we have only single particles. So we can average on time. What's happened to the particle after a lot of time. Okay? So not a lot of time, some time. So let me try to explain it to you, okay? Okay, let's look at this. Okay, that could be any function. It also can be x. Okay, but what I want to show you is that the location of the particle, let's say it's x, okay? The location of the particle is looking like this, right? It's random. It's even more zigzag than I did it. Maybe it's very, very, you see this zigzag? What does each zigzag mean?
Jump.
Collision, okay? We can think about jumps, but right now we know that because of atoms, it's actually a collision. It's not, I got to jump. No, somebody pushed me, okay? So this time scale is very short. How short? 0.1 nanosecond. And I want to ask you a question. When we're thinking about T final, okay, T final, the lungs problem, how much time it takes to the particle to be inhaled into the body? Seconds. 1 second, 2 seconds. One can even say, Ron, I know it's 4 seconds in, out, but if I want to solve the problem for 1 generation, okay, divided by 10, divided by 20. Okay, but it's still in what scale? 1 second. And what I want you to see is maybe this is unsolvable. This is too hard to solve, okay? But maybe I don't have this result. Maybe I can average the result. I can take the value here, right? Actually, let's make it bigger. The value here, the value here, the value here. Let's define a new time scale. Let's call it capital T, which is much bigger than that one and much smaller than that one. Okay, which means we have T, which is much bigger than that and much smaller than that. T final of the problem and Ti of the collision. And then I'm gonna get something like that. I'm gonna get a, you see what I got? So maybe this thing here is too ambitious. Dude, you're not gonna solve this. Come on, give us a break. But if you're gonna do some averaging around this value, you still know the dynamics of the problem. You don't know what's happening every nanosecond. Okay, I give up on that. But I can still tell the trajectory of the particle in a good approximation, right? I can do this, and to do average on time is very similar to what we did before. If I want to do average on a smiley, right, it's equal to divided by the time of averaging that I want, the total time. You're gonna sum all the results of the function smiley, okay, some function, yeah, it could be f, dt. So unit doesn't change, you have t here and you have dt here, right? You start from some location and you end up with a location plus t. So I can do average on time, okay, on all the equation and get that. If my t gonna be very big and start to get close to that, I'm gonna lose all the dynamic. We're gonna get this kind of thing. This is t final. We start here, this is the solution. No, this is not the dynamics, this is a very bad approximation. But if we're gonna take just the right time scale, okay, there's so much space in between those two, so we can average the equation. The idea is clear, do you feel me? Yes? So I'm gonna take the equation, and I'm gonna go to the next step, which I'm gonna try to average all the equation, okay? So we're gonna write again the equation, and we're gonna apply averaging of time on each term. And I remind you that the averaging is just multiplied by some constant, 1 over t, and taking the integral. Like you can do it to every term of the equation. So what we're actually getting is that. So we have the equation. Let's clean that. We have our equation. And we're gonna average every term of the equation. So we're gonna have half dx squared, right? Square dt squared minus u of the particle square equal to x multiplied by the evil fbt over m minus the 2 relaxation time of the particle, derive please the x squared. And right now I'm gonna do this averaging. I'm going to apply this averaging on every term of the equation, which means half can go outside, right? We're going to have squared dt squared, right? Squared minus, sorry, this one. Let's do that. Okay. So let's make it even clearer. I'm going to do half dx squared. So I want you to notice the colors, the different colors. Minus, this is the original equation, average on up squared. Right? Equal to x, sorry, let's say the averaging phenomena, x multiply fb t over m, x minus, and I finish with the red, 1 over 2 tau d dt x squared. Okay? And now I want you to see something very interesting. What is this? What is the average of the velocity of a particle? We can recall Boltzmann's idea, and that's what Einstein did. He said, maybe the big particle behave like the small particles with the same theory. So they said, instead of that, I can put Boltzmann constant multiplied by t, right? We don't need to take the square, the root, because we have a square, divided by the mass, not of the gas, of the particle. And this is a 1D, not a 3D, so I'm just going to put here 1. You see it? At the beginning, we solved it for 3D. Perfect. So we get rid of that. That was the idea of Einstein. And here I want to show you, is FB and X correlated? Does the Brownian motion behave differently in a different locations? Depends. If the temperature change, in stuff like that change, maybe it do. Okay? But in our case, if everything is uniform, no reason for it. So X multiplied by FBT rate them. And that's mean they are. And what is the average on the Brownian force?
We don't know, but we don't care.
We know it from experiment that the average is 0. The is 0 and also the force. So this one is equal to 0 if you wait enough time. If you don't wait enough time, forget about it. But in our time scale, this one is much bigger than Ti. So the average of the force is 0. We get rid of this term. Okay, perfect. Here, this is a constant. I can get rid of the constant, and we're gonna give up on the exact solution. We're not gonna apply the average on the derivative, but we're gonna take the derivative of the average. We're giving up. Guys, I cannot solve this, but I can solve this. Okay, so the same thing I'm gonna do here. So half d dt squared, and I give up. I surrender, but I want to get to something. Okay? Instead of say I'm stuck, I want to get to something. So if we clean everything, we're gonna get a beautiful equation. Look at that. D square dt square of x square plus 1 over delta d to dt of x squared, the average of the distance square, equal to 2kb t over m of the particle. I know this constant, relaxation time related to the drug, mass multiplied by mechanical mobility, relaxation time. I know the temperature of the problem, I know the mass of my big particle, I know Boltzmann constant. This is a solvable ODE. I can find in time what this function is. Okay? Yeah. Very good question. She asked, Ron, just to remind you, you said that 1/2 mv squared equal 3 to kb t. So if we gonna get rid of the velocity, right? We're gonna get that the average equal to 3 kb t over m. So she asked me, Ron, you have 1. Why you didn't put 3? The reason is, this is a vector. This is 3D problem. For the 1D problem, 1D, you have only 1 of this energy. Because you have a kinetic energy in that direction, and in that direction, 3D, okay? So that is the reason, and remind me that's in the end of the class. It's a very good point, okay? So we did solve it. It's very important for 1D. But if you wanted to make it 3D or 2D, you just need to change this number. And this number is here, and you see this 2? It's from there, okay? We multiply the equation by 2. So this is for 1D. What we expect to have for, no, let's deal with it. What we should have for 2D, we should have here not 2, but 4. And for 3D, what we should have? 6. So there's few options. If you want to solve a problem which is 3D, yes, you need to write 6 in this term. And also in the solution that we're going to get. Carry this 6 around. I love to do is solve the problem in 1D in each axis, okay? And then you're going to get to the same idea, okay? So that's a reason I said you're going to get it to the conclusion. But this is the ODE that Einstein got in a more elegant way, as Langevin, his French friend, did 3 years after he published his paper, okay? So let's clean that in. Okay, so the next question that I have to you is, okay, Ron, let's fucking solve the equation. It's solvable. Let's do it. We can find a solution, right? So we can do very simple. You know, this is we write it section F, which the goal is solve for sigma. That's what we are looking for. And the equation is looking d to dt of, right? Here I can put d dt x squared, right? Plus 1 over tau d to dt x squared, right? Tau equal to 2 kBt over m, right? This is my equation. I can call, I mixed the color, never mind. I can call this function f, right? And we're actually solving f dot plus 1 over tau multiplied by f equal to 2 kBt over m. Guys, this is a joke. This is a joke. You know to solve it, right? This is a joke. So this is equal to f equal to the homogeneous solution plus the private solution, right? So the homogeneous solution is going to give us some constant multiplied by minus t over tau. And the private solution, we're going to guess it's a constant, so tau moving to here, right? So the constant going to be 2 kBt divided by m, and we need to multiply by the tau, multiply by tau. And immediately I see the tau over m is the definition of the mobility of the particle, right? So the solution is f in time equal to some constant e minus t over tau plus the constant 2, which related to the dimension, remember? Dimension. B, the mechanical mobility, which related to tau and m. The size of the particle, the fluid, the correction, the geometry, B, and the energy of the flow around me, right? We see it? So this is the solution. We don't know this constant, but we can look and observe for time larger than tau, okay? What does it mean? That the exponent is dying, right? For a particle, aerosol particle, what is the relaxation time approximately? Around there, microseconds. Okay, so if you're going to wait 3 microseconds, 10 microseconds, that's it. The exponent is start to play a significant role and kill the term, right? That's the idea. So if you're going to look at the solution of f of t larger than tau, or even in the same order of tau, we know the exponents start to kill the equation, kill this side of the equation, and the result is a constant, 2bkb multiplied by t. But don't forget, we are interested in x squared, and this is the function, this is the derivative. So the final result,
The convention isn't the 5 tau?
the what?
The convention.
Okay, somebody asked me in the audience if the convention of what a good time to get rid of this is 5 tau. So it's all about approximation. 5 tau we're going to give you, if I correct right, 99.97, something like that it's close to 0. But 3 tau will also be very strong. And we didn't put a number. To be 5 times bigger than tau, it's not very big. It's not 10 times. So wait a little time after that, and you know that the solution of ft, f of t larger than the relaxation time of an aerosol, by the way, for a very small aerosol, it can be even smaller than a microsecond. Okay, so you don't need to wait a lot. Okay, so this is equal to 2b kb t, and I remind you this equal to the derivative of what we are actually interested in. So doing the integral, and voila, my friends, you got the very exciting moment. We got that x squared equal to 2, something related to the physics multiplied by t, and this something is no other than the diffusion constant, okay? And not to get confused with the diameter, because we are fluid mechanics people, so maybe you should add diff, okay? Not to be confused with that, okay? Yes? So that is a very important formula in physics, and I hope this gave you some motivation to win a Nobel Prize. And what I wanted to show you, let's write it explicitly. If you can help me with the cold water. Wait, can you pour here the cold water? So what I want you to see, let's write explicitly D, right? So D equal to what? To B KB multiplied by T. This is equal to, if you don't remember the mechanical mobility, okay, the mechanical mobility is actually CC, the Cunningham correction factor, okay? 3 mu F, the diameter of the particle, the viscosity of the fluid, and pi. And if we add the correction of Boltzmann, we also have an effect of the temperature on the problem. So we also see here KBT. You see it? So this equation called Stokes because of the mechanical mobility. Yeah, Stokes-Einstein equation. Okay? It's the fight between the temperature and the mobility of the particle to move. You see it? And that's what you should put here and also in the simulation. So I have a nice demonstration to show you here. So we're going to have the same fluid, okay, water and hot water. Okay, and hot water here. I can actually, I know the temperature. I have this device, okay, I can measure the temperature. So this is 70 degrees approximately, and this is 11, okay? And we have some particles, tea bags, and I'm gonna put them here. And we need to wait. How much time? You can calculate it, okay? Of course, there's some gravity effect, and we have more things that operate, but without touching, let's make it go deeper. Go deep, okay? So you can see here, immediately, you see how particles start to diffuse? You see, and this is because of the temperature. The D here is much, much smaller. We can look at here. So here, if I take T and make it higher, okay, this term, is going higher, and also the mechanical mobility is also affected by temperature, right? So if I have a high temperature, this go down, right? So all of these contribute, the diffusivity would be much stronger, and you can see here immediately. And the reason you see the most down below, because of gravity and not up, right? Okay? So that's what I want to show you. But of course, if the particle have some buoyancy, so gravity is not related. If we do the experiment in space or during flight, when you have acceleration in the other directions, of course, you can use this approximation very easily. Hey guys, I want you to see that here's diffusion taking place. We see that the hot cup immediately diffuse all the particle of the tea versus the cold cup that take more time. We can also see that there's a superposition of gravity and diffusion, so we have more particle in the lower part versus here. Very interesting. And the reason you see the most down below, because of gravity and not up, right? Okay? So that's what I want to show you. But of course, if the particle have some buoyancy, so gravity is not related. If we do the experiment in space or during flight, when you have acceleration in the other directions, of course, you can use this approximation very easily. We could improve our calculation by introducing gravity. And it's just going to be another constant, electrostatics, which is going to be another constant. No, actually electrostatic is more complicated, but magnetic maybe, stuff like that. We can add more terms, but the solution would be the same. We're going to take the average and get to these results. Okay, good. So, yeah, definitely. CC, this one? Yeah, so when you did the Stokes, what is CC? It's a Cunningham correction factor. Cunningham, big C, small c, correction, okay? So the idea is that when you take small particles, perfect spherical particles, but they are very, very small, the Navier-Stokes equation is not working anymore. Navier-Stokes equation assume continuum flow, okay? Not a wall that built of particles, but a smooth flow around the sphere. So all the theoretical model is falling apart. Is falling apart immediately? No. Degradation to it. So CC is a function, which depend on the ratio between the diameter of the particle versus 2 times the mean free path, also known as Kuhn-Desson number, which is non-dimensional number that tell you how much close you are to a continuum flow. Okay? So this is just a correction when you go small. What I want to show you right now is some comparison to understand. So what I did here, you know, breathing take approximately 1 second, 2 seconds, but the scale is the same. So I want you to see that for big particles, you see 50 micron, okay? Because of diffusion, particle actually diffuse in 1 second, approximately 1 micron. Okay, I'm 50 micron. I'm going to wait 1 second. I'm going to diffuse 1 micron. Versus gravity, which falling in 1 second, 50 micrometer would fall 71 thousandths. Okay, micrometer. So you see that who is govern the situation? Gravity. Okay, but when you go down, down, down until the half micron. The half micron, 0.5, they become the same. Look, from gravity free falling due to terminal velocity, 10 micrometers. And from diffusion, 11. So in a half micrometer, which is the size of bacteria, the game starts to change. Okay? It's moving toward diffusion. So you see that these 4 small particles, you can forget about gravity at all. Diffusion would jiggle the particle around even up against gravity. You see it? The collision, look, this is 2 orders of magnitude more. Okay? This one, look, for very small particles, diffusion is governed the situation, and we can think about that oxygen is a very diffusive particle. Very. O2, N2, very diffusive because they are very, very small. And for that reason, they succeed to deposit inside the body and we can breathe them. Okay, that's the idea. And very small particle is very good for drug delivery because diffusion is very, very strong. However, it's very hard to produce these small particles in a day-to-day devices. Only in the lab infrastructure you can actually control these small sizes. So this is a big challenge when you think about it in the inhalation world. And people try to get very, very small particles, but they not always can do that, okay? That's a problem. The last part I want us to do is do some dimension analysis, okay? It's important for us to understand when diffusion is very govern the other mechanism. So the table that I show you is, for my opinion, is the best, but we should do also a more rigorous idea of it. So let's do some summary about non-dimensional so far, which is gonna also help you with the homework. Because in the next homework in the MATLAB, what I would really want you to do is to plot all the non-dimensional numbers and get a feeling. Okay, so in each generation, what approximately I expect my numbers to be. Okay, so what I'm gonna write here is the number. Okay. Here we're gonna write ratio of, and here we're gonna explicitly say the math, yeah, what we need to do actually. Okay, so remind me the non-dimensional numbers that we learned so far. Let's do a summary. Reynolds, perfect. So what does Reynolds tell us? It's a ratio between two identities, which are, again, inertia, very good, inertia, yeah, inertia, going that direction, right? Versus viscosity, right? Versus viscosity, the boundary condition, the friction, right? Try to stop you. So each time that we want to present this ratio, we need to choose some physical, not math, but physical properties. So I like to present Reynolds as a ratio of, as people say in the audience, of pressure and stresses, right? So I think the inertia is pressure and viscous as shear stresses. And if we're gonna plug them in, we're gonna get rho u d mu, where d is the airway diameter, okay? Not the diffusive term. What another number we learn? Again? Yes, not what I wanted to say, but about particle dynamic, not flow. This was about the flow. And we need this Reynolds to evaluate the drag around a sphere, or to know that if the lung, we have a laminar flow, right? Or turbulent flow. Crazy chaotic flow, okay? But also Stroll is a good idea. Stroll talking about the time, how much I react to the time of the inhalation. But let's assume steady state. What another non-dimensional numbers we learned so far? Huh? Stock number is a great example. What Stock represent? Stock number. Again, inertia or momentum, the flow, but of the particle, okay? Of the particle versus the convection. What is the convection? Convection is the propagation of air. The air wants to take me that way, but I have this much inertia, this high mass and high velocity. Not necessarily I'm going to follow. So I like to present this ratio as distances. S is the stop distance. How much time, how much length it's going to take me to stop. Think about a car, driving a car. Oh shit, something that I need to stop. You know, this drift that the car is doing. This is the stop distance of a particle when in the surrounding there's a change in velocity. How much it takes him to react to that versus the geometry of the problem. Characteristic length, the diameter, the turn. So usually in the lungs we put the diameter, right? Good, another one. You need this for the homework, another one. We learn about also H. What was h? We call it the gravity number. It represents the gravity effect on a particle versus the convection. Okay? How fast the flow going to take? Convection is this. Convection. Convection is the flow that carry the particles. Okay? You want to take it with him, right? Versus gravity. The gravity want to take the particle downstream. In the case of Stokes, you can think about that idea, that the convection term want to take the particle to take a turn, but however, the particle has some momentum, and it's not necessarily will succeed to do it. Okay? So convection were in both of them.
So you're missing an N.
What?
Convection?
Convection, yes. Okay? Convection. Okay? So this one I like to present with velocity. Okay? Each one can do whatever you want. Okay? So gravity, what velocity describe gravity? Terminal velocity. Right? So tau g divided by convection is just the velocity of the flow, which we usually take the average velocity. Right? We need some representative. Of course, the velocity change. Okay? So we got that. Of course, we can also, I cleaned that. We can also have the Froude number. Somebody remember what is Froude number? Huh? Again? Froude number is inertia versus, I want you to think it that way. Okay? Non-dimensional number is presenting something against something. Always, okay? Reynolds, it's inertia versus viscosity. I want to get inside, I want to continue with the flow, however, viscosity tries to stop me and turbulent me, right? Sorry, inertia want to turbulent, viscosity want everything to be organized. Near the wall, zero velocity, please. In the middle, maximum velocity. All the layers should be organized. This is the viscosity. Inertia said, fuck that, I want to get to the other side. So there's a fight between them. If it's very big, chaos, okay? If it's very small, viscosity, the mu going around, make sure that everything is in place, very easy to solve, right? Stokes is again, is a ratio. Inertia, I have a lot of momentum, a lot of velocity, nobody gonna stop me, and the flow asks, can you go to the right? Can you go to the left? Can you stop here? I don't know, it depends on how much inertia do I have. H number, the convection wants to take me along the tube. However, maybe gravity would say, the particle gonna deposit here. You're not gonna continue with the flow. So here's the ratio, okay? I can also compare, use Froude. Froude is comparing, look, inertia by gravity, okay? So you can try to come up with the ratio, but you can also you can take Stokes versus H. And what would happen to the convection if I'm going to divide this by this? Going to cancel out, okay? And it's more, it's usually they do the square of the Stokes to H. Historical reason, it doesn't matter, okay? Square root. So what would happen, the inertia, convection versus gravity, convection, right? And convection cancel out, and you left out with inertia versus gravity. You see what I mean? So if you know this is the main player, you can go Stokes. And now let's introduce the one and only non-dimensional we've been waiting for. The number present, the fight between convection and diffusion. So convection and diffusion. And now we're facing a problem. How we can define convection versus diffusion? We need to look to two properties, the same properties with the same unit, and make a ratio between them, right? One would present convection and one would present diffusion. If you're going to look into the equation, we work so hard to develop this one. I see length and I see time. So I can easily understand what is the length of convection, what is the time of convection, and more challenging is to find the same parallel one in diffusion. But we have the equation, so we can play around. So I'm going to go to the last board there. So here it is. So we're going to define Paclet, and Paclet is very important. If, for example, this tea bag was inside the tube, if you have a syringe, think about syringe inside the bloodstream, and you want the syringe medicine to diffuse in the blood, you must calculate the Paclet number, right? You want to make sure it diffuses in the time scale that you want, in the rate that you want. So every time people mix fluids and do this stuff, this Paclet number is a big hit. So what I like to do is define Paclet with time ratio, okay? 2 different times. And I want you to be very, very careful about it. So when you do velocity, and when you do distance, and when you do shear stresses, there's no question who should be in the denominator or up and down, right? It's very easy. So Paclet number, let's just make it clear, it's convection versus diffusion, okay? So let me ask a question. If diffusion happened really, really fast, immediately, in a very short time, it means the diffusion is very strong, right? If gravity happened very, very fast, boom, immediately, it doesn't go into the airway. It immediately falls. It's happened very fast. So it means gravity is strong. So in time, something very funny happens. So the smaller the time, the stronger the phenomena. You see what I mean? Versus the other mechanism, right? So if I want to present the time for diffusion, I need to put it the other way around. There, right? And the convection here. You see what I mean? It's opposite. Why it's the opposite around? Because we actually talking about the rate of the effect, right? So the rate, the tempo of the effect, the beat of the effect, right? So that's the reason it's the opposite way around, okay? So what is a time for diffusion I can use? We know it to be looking there, right? So I can use the equation that we came up with. T for diffusion is, looking there, right? It's L squared divided by dt, right? The diffusion. Note that I did not put here the 2, okay? Because it's not a dimensional number, I just want to say if somebody's thousandth time more than the other, 2, 3, 6 would not be that significance, right? 2 divided by d, right? Yeah, this is. And for the convection, what can I use? Convection is time is distance divided by velocity. So d of the airway, right? Divided by average velocity. That's true, right? And also for the length scale here, I'm talking about to diffuse in the airway, right? Which means to diffuse to the sides, right? So this is the distance I'm talking about for diffusion. Agreed? Agreed? Yes? Do you see what I mean? So I changed the length scale to be the same. I can reorganize the equation. And what we're going to get, U going up, U average going up, D diffusivity in the denominator, right? And this one cancel with this one, the airway. Right? So this is the Paclet equation, the Paclet non-dimensional number. He tell you how much convection overcome diffusion. You see what I mean? If this number is very big, it means there no diffusion. Okay? If this number is very small, diffusion. Okay? You got it? And you're going to see this number in the lecture. Because just we're right now going to talk about particles, and not particle, but something that you breathe, and you want to see how it's distributed inside the flow. So you go. What is the units of D? The diffusivity? meter squared divided by second.
Okay.
This is meter. This is meter per second. So we okay. It's a non-dimensional. It must be non-dimensional because we started from a ratio of non-dimensionals. I had there 2 points. I want to show you that you can use time, but don't forget that the time is the other way around. Okay, because you're actually looking at rates and tempo and beats, right? So you just need to flip it. So that was the tutorial about diffusion. I hope it helped you for the simulation. And also I'm going to release a